Hi everyone, welcome back to Chem Story. In this chapter, we're going to explore a simple but powerful tool, the degree of unsaturation, that helps us predict molecular structure faster. It's a concept that might seem small at first, but it gives us big clues about what a molecule could look like, even before we draw it. So let's break it down step by step and see how it works in real examples. Let's start by clearing up what we mean by unsaturated. An unsaturated hydrocarbon is a molecule that has at least one carbon-carbon double bond or triple bond. And because of those multiple bonds, it ends up with fewer hydrogen atoms compared to a fully saturated molecule, like an alkane. So basically, if a hydrocarbon seems to be missing some hydrogens, it's probably unsaturated. The degree of unsaturation, also known as the index of hydrogen deficiency, tells us how many rings and pi bonds are in a molecule. It's a quick and powerful way to get structural hints just by looking at the molecular formula. And there are two main ways to figure it out. One is based on the molecular formula, and the other is by analyzing the structure directly. Let's begin with the formula-based approach. Now let's take a look at how we actually calculate the degree of unsaturation from a molecular formula. Here's the basic idea. We're comparing how many hydrogens a molecule should have versus how many it actually has. If it's fully saturated, like an alkane, it follows the rule CnH2n plus 2. That gives us the maximum number of hydrogens. So here's the formula we use. Maximum number of hydrogens minus the actual number, then divide by 2. And when we put that into a general equation, it looks like this. du equals 2c plus 2 minus h, all divided by 2. This gives us the total number of rings and pi bonds in the molecule. It's simple, but incredibly powerful once you get the hang of it. Let's try calculating the degree of unsaturation for this compound, C6H10. Using our formula, du equals 2 times 6 plus 2 minus 10 divided by 2, which gives us 2. So the du is 2. That means this molecule has a total of 2 units of unsaturation. It could be 2 double bonds, 1 triple bond, or maybe a ring plus a double bond. Now let's look at C8H14. We'll plug it into the same formula. du equals 2 times 8 plus 2 minus 14, divided by 2, which gives us 2. Again, we get a du of 2. Even though it has more atoms, the total number of rings and pi bonds stays the same, 2. Here's one more. C10H22. Let's apply the formula. du equals 2 times 10 plus 2 minus 22, divided by 2, which gives us 0. This time, the du is 0. That tells us the molecule is fully saturated. No rings, no double or triple bonds, just straight or branched alkane structure. Sometimes, the molecular formula includes atoms other than carbon and hydrogen. So, how do we deal with those? Luckily, there's a simple rule set we can follow. If the molecule contains a halogen, like chlorine, bromine, or fluorine, just count it as if it were a hydrogen. One halogen atom basically replaces one hydrogen when calculating the du. Now, if you see oxygen or sulfur, you can ignore them. They don't affect the number of hydrogens in the way we care about for this calculation. Nitrogen and phosphorus are a little different. In this case, you treat each NRP as if it were a carbon-hydrogen pair. So you're adding both a carbon and a hydrogen to the formula. That way, we can still use the same formula, no matter what atoms are involved. And with just a few tweaks like this, you can handle even complex molecules with ease. Let's try a few more examples, this time including atoms other than just carbon and hydrogen. First step, we've got C6H11Cl. Chlorine is a halogen. And in degree of unsaturation calculations, we treat halogens like hydrogen atoms. So we imagine replacing the Cl with a hydrogen, giving us C6H12. Then we plug it into the formula, 2 times 6 plus 2 minus 12 divided by 2 gives us 1. So the degree of unsaturation is 1. Next, look at C5H80. Oxygen is one of the atoms we ignore, so we just calculate the du based on C5H8. Using the formula, we get 2 times 5 plus 2 minus 8 divided by 2, which gives us 2. so the du is 2. Now, here's an interesting one. C8H9N. Nitrogen gets replaced with a CH unit, so we treat the molecule like C9H10. Then we plug it into the formula 2 times 9 plus 2 minus 10, divided by 2, which gives us 5. So this molecule has a degree of unsaturation of 5, which suggests a pretty complex structure with multiple rings or pi bonds. Now, here's a more general formula we can use, even when the molecule has atoms other than carbon and hydrogen. The unified formula is 2C plus 2 plus N minus H minus X, all divided by 2. C is the number of carbons, H is hydrogens, N is nitrogens, and X is halogens like chlorine or bromine. Oxygen and sulfur, we just ignore them. They don't affect the du. This version lets you calculate the du for pretty much any molecule. Let's try it with a few examples. Let's try a few examples using the unified formula. First one, C17H21NO4. Just plug the numbers into the formula, and you get a degree of unsaturation of 8. That means this molecule has 8 rings and pi bonds in total. Next, C5H10NCl. Same idea here. If we apply the formula, the du comes out to 1, so this structure has just 1 ring or 1 pi bond. Simple as that. These quick checks give you helpful hints even before you start drawing the structure. When we're looking at the actual structure of a molecule, there's a really simple way to figure out the degree of unsaturation. Just count a few key features. Each ring adds 1 degree, each double bond adds 1, and each triple bond adds 2 because it contains 2 pi bonds. So the full formula is number of rings plus number of double bonds plus 2 times the number of triple bonds. That sum gives you the total degree of unsaturation based on the structure. Now, if you take a closer look at that formula, you'll see that it's basically just counting how many pi bonds are present in the molecule. Double bonds have 1 pi bond, triple bonds have 2. So when we multiply the triple bonds by 2, we're really just adding up the total number of pi bonds along with the rings, which also contribute to unsaturation. That's why this method works so well when analyzing structures directly. Let's take a look at some structures that each have a degree of unsaturation of 1. This means there's either 1 double bond or 1 ring in the molecule. On the left, we see an alkene with 1 double bond, and on the right, we have a cyclohexane ring. No double bonds, but the ring itself contributes 1 degree of unsaturation. So even though they look different, both molecules have the same degree of unsaturation. Now let's look at a few examples with a degree of unsaturation equal to 2. That could mean 2 double bonds, 1 triple bond, 1 ring plus 1 double bond, or even 2 rings. As you can see, there are multiple structural possibilities that give the same du value. Finally, here's an example where the degree of unsaturation is greater than or equal to 3. This is testosterone, a complex molecule with multiple rings and double bonds. Just by looking at the du, we can tell this molecule has several elements of unsaturation. But when the du gets this high, there are many possible combinations of rings and pi bonds, so we'll need more information or the full structure to figure out the exact details. Alright, that's it for today's lesson. Thanks for tuning in, and I'll see you in the next one.